Hey, welcome back. So if you remember last time we started talking about front end, and the last thing we wanted to talk about we couldn't finish was the issue of renaming. And if you remember, I told you that essentially we have three type of dependencies. We have read after writes, which is what we call a true dependence. This is indeed the dependence that we cannot really avoid. But there are two other dependents that doesn't really aren't really dependents. They're just made up dependents, which we call false dependency. One was write after write, and the write after write was happens because you happen to write on the same register twice. And then the easy way to avoid this was just renaming and changing the name of one of the registers to another. Same thing happens with write after read, which again, if you are writing to something in later stages of your program, you can just easily just change the registers. So this anti-dependence and output dependence is the things that we need to fix. And the reason that we need to do this because we want to kind of decouple these instructions so that we can do more out of order execution, right? We could have just said that, oh, whenever we have anti-dependence and whenever we have false dependence in general, let's not reorder them, but there is no reason that we need to do that. We can easily change them as long as we change the registers, okay? So this process is what we do for the renaming, okay? So what's the idea of the renaming and why renaming would work? Renaming is actually bank on this additional concept called physical registers versus architectural registers. So the difference between them is when we are writing an assembly code and generally when we are using an ISA, we use different registers. If you remember, I told you that any instruction is essentially just, a sequence of commands and some operands, right? And then kind of inputs to this commands. And this operands could be just a plain value, which we usually call immediate. It could be registers, which we use in RISC-V kind of language, or I say we use it as x0 to x31. Or it could be memory addresses, right? Which we usually use it as like some form of M and some number inside, right? And then this middle one, the register one, is the kind of the registers. And again, in RISC-V architecture, we have 32 registers because in the instruction, we actually need to kind of define the number, right? So we need to know beforehand how many registers do we have and then assign correct amount of bits inside our instruction to address each one individually. That's why, for example, if you have 32, we need log2 of 32 in order to show them. That's why we need 5 bits to, for example, show RS1, RS2, and RD, right? And I cannot tomorrow say that, you know what, I want to do 64, because if I want to do 64, then I need to add another bit. And if I add another bit to my instruction, then I need to kind of figure out where should I put this one bit. I should entirely change my decoding, my compiler, my software, my operating system, everything has to change. And remember that this usually is fixed, right? This is 32 bits in most cases. So it's not like, you can easily change the size of the registers. You're kind of like, you're kind of limited and constrained by the size of the instruction and the kind of bit width with your registers and so on and so forth. So in other words, you're kind of like you have to stick and stuck with this 32 number of registers, okay? This is what we call architectural registers because this is at the architectural level. At the ISA level, this is the number that we see and we cannot really change, okay? But in fact, in hardware, if you remember, I told you that essentially the idea of registers are these, we usually call it register file because we put all the registers into the storage system that we have in the processor. And if I, for example, tomorrow I have better hardware, nothing prevents me to kind of like add more and more registers to this register file, right? Like more and more registers. The trade-off, of course, would be more area, more power consumption, and so on. But, as we move from older generation to a newer generation, the more we add these other features, one thing that we probably want to do is increasing the size of my register file, right? Adding more and more registers, But then on the other hand, it's kind of like this, it dictates that I can only do 32. So this is where we have this idea of, we call these architectural registers, and we call this physical registers. The physical registers, the actual registers that we have in our system. Of course, at the beginning, this has to be 32, cannot be less than 32, otherwise, weird thing will happen. But maybe we can find a mechanism that we have more than architectural registers, and kind of like find a method to dynamically map one architectural register, one physical register to multiple architectural registers. In that case, we kind of virtually increase the size of our architectural registers, okay? This is the process of what we call renaming, and in the process of renaming, now we can actually fix the issue of anti-dependence, output dependence. We can also leverage the fact that we have more registers that we want, potentially making things faster, okay? So again, this is kind of like, these are the things that we are, I'm writing here. For example, I'm just giving you a few examples of these false dependency. That, for example, if you have things like loop body or like, anything that's kind of like, keep using something over and over, that creates lots of false dependence that you don't want. There are things you can do in order to reduce false dependence. For example, you can do loop unrolling, you can use function calls and all those things, but they can only help a little. They cannot really fundamentally fix this issue, okay? So instead of like going through some form of software method to fix this, the best way to go about this is actually implementing this kind of architecture to physical register conversion inside the hardware. So we bake this into the hardware, and that would be what we call renaming stage in our pipeline processing, okay? So this is kind of like, just a summary of this, that remember that we still gonna have raw data hazards. This is true dependence between registers, and renaming not gonna fix that issue, but what it's gonna fix is that it's gonna fix the false dependencies. Yes.
On the last slide, you said that unrolling can only help a little bit because you'll eventually run out of register. Why is that? I mean, assuming like, the first time the loop is called, it will finish before you run out of registers.
It might, but like you never know. If you have a complex loop, you might have many registers inside. Or there is also like, if you have function calls within function calls, you need to reserve some registers. You have some other registers, and you cannot, at any given time, you cannot use all the 32, right? Some of them are safe for some other spots, functions and all. So, you can, it helps, but it's kind of like effectively you kind of like have 8 registers kind of thing, and you need to deal with the 8 registers. In many cases you can, but in many cases you couldn't.
Got it. Thank you.
All right, so as I said, this is the process of what we call register renaming, and this happens during one pipeline stage of the processor. We have architectural registers, or usually we call them AREG, and then we have physical registers or PREG. And the idea is that if I can map multiple of if I have, let's say, x0 all the way to x31, if I can map multiple AREG, one AREG to multiple physical registers like P1, P2, P3, is as if that I have access to all 3, and then many more registers. And then this way, if the mapping works, I can just increase my physical registers as much as I want without really any issue. So how does this work? There are 3 things that we need to kind of like, think about when we are doing, renaming, right? The first is, of course, the mapping strategy. What's the logic that we're going to use to assign a PREG to an AREG? Then we need to kind of keep track of this mapping. We need to know when to allocate the new registers, when to free a register. So essentially we need an allocation deallocation mechanism. And lastly, we need to maintain the states, because in many cases we need to kind of roll back our processors, we need to flush things out, and we need to kind of go back to certain stages. If we make a mistake, we make a speculation. If you are kind of like, doing some form of context switching from one process to another process, There are many instances that we need to remember the state of this mapping, or we need to kind of go back to a previous mapping, right? So we need to kind of like have a mechanism to kind of recover that. So this is the three main parts of any sort of renaming strategy that we're going to have. And I'm going to explain two main strategies that, modern processors are going to use. One is what Boom is using and many other processors are using, and the other one is many other processors, but not Boom is using. So how do we do renaming? Let me just give you one example, and then I'm going to take a step back and give you both options and then describe the other one and then compare the two. The one that we probably have seen, and you've seen it in my class as well if you've taken the course or if you watch the videos. We usually use this kind of like, register alias table or RAT. What does RAT do is that think about RAT as a table that has entry per architecture register. So if you have like 32, we have 32 entries. And in each one, we kind of stores the most recent mapping between A-reg and P-reg. Remember, one architecture register might be mapped to multiple physicals. So in other case, there could be multiple numbers per row, but in RAT, we usually just remember the most recent one, and we put it there. Then what we do is essentially we kind of like have another pool, which we usually call free pool. These are physical register that hasn't been assigned to any of the registers. But the next time that we need to do the renaming, we go to that free pool, we bring one of these physical registers and put it into the new mapping. We remember the previous mapping in some other reserved, RAT, or some other methods that I'm going to explain. And then we just keep continuing doing that whenever we need to do the renaming. If you want an example, let me just again give you a quick example. This is what we covered extensively in the past course, but I'm going to give you a quick example. But this is just remember, this is one way of doing it. There are other ways as well. In our example, let's say we have only 5 registers. So I'm not going to give you the 32. Let's say we have only 5 registers. This is your architecture register. So let's say, for example, X1 to X5, and let's say we have 10 physical registers. So effectively, we can have 2 per physical registers. So as I said, we have 2 tables, the RAT table and the free pool table. And in the RAT table, we have the architecture registers and the physical mapping, the most recent one. We usually also use a trick to kind of remember the previous mapping as well, because for recovery, we need to do that. But in effect, there are actually RAT itself is kind of, you can consider it as 2 tables. That one is the most recent one and one is the kind of the backup one, okay? So how do we do that? Let's say that the initial mapping is like this. Doesn't matter. There could be any other initial mapping, but let's say initially it looks something like this. That X1 is mapped to P1 and so on and so forth. Then let's say, for example, we have this sequence of instructions and we need to map this and rename this based on this RAT that we have. So here's the algorithm that we are using. So essentially, when we are doing the renaming, we only assign a new registers when we have a destination register. The reason for this is that, remember, we want to get rid of these kind of write after write and write after read ones, right? So whenever we see a new destination register, when there is something needs to be written to the register, we change the number and assign a new number. And this way we kind of eliminate the need of having this write after write or write after read dependencies. For the source registers, no need to change anything, so we keep using that. So for this case, for example, if you look at the OR instruction, if you remember, these two were the source registers. For the source registers, all you need to do is going to the RAT and see the most recent mapping. So in this case, for X1 is P1 and for X2 is P2. This is your registers that you're going to use. These are your source registers. And as I told you, now we need to map a new free register to X3. So we're going to replace P3 with one of these free registers. How do we do that? We usually kind of like start from the top, or we can just randomly pick, doesn't matter. I mean, for this particular example, we can start with this. So we put P6 here, okay? So what will happen is that we remove this P6 from the free pool. P6 is no longer free, is assigned to something. And then what used to be P3 is now P6. Now the question is, what will happen to P3? What will happen to P3 is that we hold on P3 until we make sure that this instruction indeed will be executed. Because again, remember that many instances of many instructions needs to be kind of, replayed or flushed out of the pipeline. Once we make sure that indeed this instruction, this OR instruction is going to be what we call retired, which I'm going to explain next week, then we say that, okay, this mapping going to be the same mapping, so I can get rid of P3. So essentially the old destination register, in this case P3, going to be freed once we make sure that this OR instruction is indeed going to be executed. And again, how do we know that? This is the concept of what we call retire, which we're going to explain next time. For now, just remember that P3 going to be saved in another RAT, in reserve RAT, and then whenever we think that it's safe, we're going to let it go, okay? And then we continue doing that for the others. For example, for this app one, so we go to X4 and see P4. We're going to go to X3, and then remember that we have a new mapping for X3, right? So it's no longer P3, it's now actually P6. So we put P6 here, and then X4 now needs to be renamed. So what used to be P4 now should be P7. So I put P7 here, okay? And this would be for add, and then I can continue for all these others. To kind of like, this is the logic for all of them. You can follow it and let me know if you have any questions. But we can continue doing that for these other instructions. Maybe do this yourself just now, and then I can show you how we do it. Maybe one minute for you guys to practice. How do you do the renaming for these next two instructions? All right, so the answer to both is going to be something like this, right? So X2 would be P2, X5 would be P5, then you rename X3 again. And then for the ADA instruction, this 2 is an immediate, it's not the register. So of course you don't need to rename an immediate, but X3 would be again P8 and then P9 and so on and so forth. So you just continue doing that. At some point, some of these instructions will be executed and you will free those older registers. So these older registers will come back to this free pool at some point in your system. Yeah.
In the second line, why is X4 turned to P4 or renamed to P4?
Here?
Yeah.
So you mean these are architecture registers, you always have to find the physical mapping of any register, right? So again, if I go back here, when we start here, so you need to see what is the mapping between architecture to physical, right? So for source registers, you go to the RAT and whatever mapping it says it is, then you're going to use it, okay? So in this case, it's P1 and P2. In this case, for example, is P4 and P3, okay?
So that's
So-
what you were saying, like the source registers don't change or
Yeah, don't change. Don't change as in like you still do the mapping between the physical, because the physical is the one that you're going to use, but you just assign a new register to them.
Do we have to rename all the destination registers?
You always rename destination registers. Yes,
and that one you just pick a free one. The
you pick the first free. Any other questions? Great. Yes. So So this is, as I said, one way of doing the register renaming. This is what we call explicit renaming logic. That is when we have a physical register file and then we kind of read off of the physical register file. This is what Boom Core also does, and many other processors also does. The alternative to this is what we call an implicit or in ROB data in ROB design. So the difference between the two is kind of like this, the implicit versus explicit. So what you will see here is that, you know, this top part is what the fetch was. And if you remember, this was kind of our fetch buffer. Okay. Now we're going to the decode rename part, right? And then we have this structure called reorder buffer. Again, the use case of reorder buffer we're going to get into next week. I'm not going to go through what exactly why we need reorder buffer. I mean, very quickly, if you remember, I told you that we kind of fetch and decode instruction in order. Then we execute things out of order. But once we are done with them, in order to make sure that things happens in the correct order of programming, we retire them in order. And this is where we're gonna reorder them. This part we call reorder buffer. It's some buffer that you put things back in the order that it's supposed to be. Okay, so this part is what we call an reorder buffer. So reorder buffer itself is a kind of, think about it as a buffer, as a storage unit. Okay, so you have two options for storing your values. Okay, you can either store your values with the kind of tag and every metadata that you want in the reorder buffer. This is what we call the implicit, renaming logic, which where you have your data with the instruction inside your reorder buffer. Or the method that I described and showed you the algorithm is you don't store the data in the reorder buffer. You actually access literally the actual physical register file when you need it, and then execute things off of there. Okay. For this, you need to kind of like, have some tags and knowing what is mapped to what, and you need the rat and all those things. For this reorder buffer, things are a little bit easier in terms of keeping track of things, because you just read your register file once and put everything into the reorder buffer, and then you move on. You don't need to keep track of rats and multiple rats and changing rats and all those things. So the difference between the two is, here you do the explicit and reading it from the physical registers. Here you're kind of implicitly doing it by just reading the data directly into the reorder buffer. Okay. So what are the trade-offs and what is kind of like the difference between them? The explicit one, the one that we described earlier, the good thing about this is that you have one unified register file called physical register file. So every architectural registers is translated or mapped into the physical. Now everything is physical, and then you read the physical registers when you want to. And then, of course, for that, we need a mapping, which we usually call RAT. The problem with this is for every branch, for every time that we need to kind of recover things, we need to take a copy of our RAT. Okay, so we don't have really one RAT. We have many different RAT, many copies of RAT. The amount of branches that we want to have, we have to copy the RAT. So there is a storage overhead that comes with this format. But the good thing is that on misprediction, exception, recovery, generate, anything that we need to revert back, we just keep the RAT that we want and then just discard everything else. So very quickly we can find the RAT, copy everything, and then move back and then continue doing the execution. Okay. So it's kind of like the recovery would look like something like this, that let's say this is the sequence of instructions. We have branches, different colors of branch. So what used to be one RAT is kind of like now 4 RATs, right? For every branch, you get a copy of your RATs, and then you also have a copy of your free pool every time that you're doing it, right? So on the misprediction, what we should do is that, of course, we need to flush all the instructions. We need to deallocate all the RATs. We need to recover the RAT that we want. So for example, let's say if this was the misprediction, we get rid of this, and then we recover it from this kind of purple one, and this would be the rat that we need to use, and then we resume from there and then continue doing. Okay, so that's kind of the idea. Yes.
So when you do that, how do you ensure that when you flush
Mm-hmm.
that and you go back to your checkpoint that you don't, that you haven't overridden registers that were in the the checkpoint of that table. So that's like you lose data because you overwrote registers.
Good. This is a good point. So when we are doing the rat, when we are doing what we are doing is that the register file that we have, you also copy that register file as well. So when we are saying that you copy things, you copy your physical register file, you copy your rat, you copy your free pool, everything. Whenever you see a branch, everything there will be a copy from it. So we usually have what we call a messy register file and a cleaned register file. When we are, sure that, things are moving forward, then we copy it. We didn't discuss it here because that's part of the execution, which we're going to discuss next week. Well, that's good observation. Questions? Good. So what are the challenges? Of course, we need a checkpoint for every single kind of speculation or every single branch. So the big question becomes like, what if you have many branches? Like, what will happen? So essentially, what you would need, a worst case scenario, is that if you have a code that is just this, right? If you have a code like this, then you need this many checkpoints, right? In other words, I need one checkpoint per ROB entry, because ROB entry is the amount of instructions that I can hold. Let's say 96 or 128 or whatever. I need that many capability of having that many checkpoints in our systems. Although you don't necessarily need to have that many, you can have less than that. The question would be, what should we do if we have less checkpoints that we need? That's where you kind of stop speculation. So you stall. So for example, let's say that I have maximum of 4 checkpoints available. And if I run something like this, that, 1, 2, 3, 4, so I have all of my 4 checkpoints, and now I'll see the 5th branch. Once I see the 5th branch and I see that I don't have any more storage to checkpoint, then I will stall the processor at this point. I no longer do speculation. I'll stall the processor at this point to these things to be resolved. Then you can free those kind of checkpoints, and then you can continue doing your normal execution. Okay, but usually this rarely happens. If you have a high-end processors, you can have more checkpoints, right? This is again the trade-off between performance and area, air storage, and power. If you have enough of these checkpointing, then you're good to go. Okay. Another creative method that you can do is you can selectively checkpoint things and say that, okay, for high confidence branches, maybe I don't need checkpoints. I'll probably just jump back to the previous checkpoint. And then for low confidence branches, I'm going to have a checkpoint. So for example, let's say I have branch, and then I take a checkpoint for here. For this one, I can have a checkpoint, but maybe I can say that, you know what, this 99% of the time, this is correct. So I don't have a checkpoint for this, but maybe this one is also, I'm going to have a checkpoint, okay? Because I'm not sure about this. So what will happen is, if this branch is indeed predicted correctly, I'm saving one checkpoint here. And if indeed I make a mistake, I always have kind of like a mechanism to go back. The penalty I'm paying is that what used to be 1 checkpoint is now 2 checkpoints, so you're kind of like doing it twice. But at least I'm kind of saving on this checkpoint. And again, if this is very high confidence branch, I'm saving a lot. Question?
Yeah, so for every branch, you're not only copying the rat, but you're also copying the entire state of the processor.
Well, we're gonna get to the execution unit and you will see what else you need to copy. For now, you just need to copy the mapping because we're just talking about the renaming. But yeah, you need to copy many other things.
Okay.
Yes.
Isn't it a finite number of clock cycles until your branch resolves?
Yes.
So you would only need like a handful of checkpoints or, right?
Depends. So your argument is that you know it's always like there is like 10 cycles difference between them.
Yeah.
Not necessarily. Like for example, if your branch is based on the value of some memory, like if it's something like this, if X is bigger than M address, right? Something like this. Now, if this M address is not in your cache, it's actually in your DRAM. So you have to wait for this value to come back from the main memory. So you wait for the operands to come. If the operands is in the registers, sure, then it's few cycles. If the operand is in the memory, then you have to wait, right? So, and then things could be also like very, like think about all these kind of like, you know, very nested kind of like deep branches that are like, you know, if then else, like case, switch cases. There are many of instances like this that things can be like very, very quickly gets, you know, very nested. So it's a possibility. All right. So yeah, so you either kind of selectively checkpoint and then pay the penalty if you made a mistake, or you stall a processor and then you can move forward with that. Okay. So the other alternative, as I said, is implicit. The implicit means that, you know what, actually, I'm not gonna like, you know, hunt the reading from the physical registers. Whenever I see the instruction, I'm gonna go into my register file and actually read the data and put it into my ROB. The good thing about this is that you don't need to copy this RAD anymore because you have the instructions and you have the data inside your ROB. If you want to flush, all you need to do is essentially invalidate that entry in your ROB. Like very straightforward. You need only one RAD for this. The problem with this is that now you need to kind of like, you know, keep track of tags. You need to actually store all this data inside your ROB and all those things. And then sometimes this reading from this register might be an issue. In some cases for forwarding, you need to kind of like do all the forwarding with this. So there are additional penalties that comes with this in your system. That's why, you know, in many systems you actually don't use implicit, but actually use explicit renaming. Okay. Any questions from implicit and explicit? Yes.
If you said that for the implicit, you already keep track of the data in the ROB. Why do you still need a RAD?
You don't need a RAD. You need one RAD, right? You need one RAD to kind of know what is the mapping, because remember, again, you still save what your register file is physical register file, right? So you need to know what is what and then how you kind of like save those. But other than that, you're good to go. So essentially, think about this. You have one register file. What you do is like, you know, based on let's say it's X3 or whatever. You go to the architecture register file and see what this is mapped to into the physical register. You read that and you put it into the data, and then you move forward, right? So what is implemented in Boom? In Boom, we're gonna do the explicit, as I said. So we're gonna have the map table here. And then essentially, if I have a bunch of different instructions, since this is a super scalar processor, as I said before, you can have multiple of these map tables, right? And then you will have also your free list. And then what you will have is essentially kind of like, you know, read the mapping, and then the bypassing also happens here for the free list. So this is just the logic to whether we are selecting this register or are we like replacing it with a free register. That's really what these parts does. remember that we need to do either renaming, like, assigning a new registers from the free pool or using existing registers. This logic here is kind of doing that for you, okay? And let me see. So there is also this busy table, and this busy table essentially is kind of telling you which registers are dependent and which registers cannot be freed. Those that are not busy anymore can go to the free list. So it's kind of like that's how we keep track of what is what. And then another thing that busy table will help you is that next week when we start talking about scheduling, we need to know when is the time for registers to move forward to this to the execution unit, and this busy table kind of tell us when that happens. So this is the story of like next week when you're talking about scheduling. So yeah, so these are some details. Again, the free list tracks the physical resistors. And then let it to pass through the rename stage. The free list is kind of like a bit vector essentially, right? So it's like you need to just, save zeros and ones for each register. 0, for example, means it's free. 1 is not free, or the other way around. Then we're going to use what we call a priority detector, which kind of like decide which of these registers can go, or you can just use random assignments. Doesn't matter, whichever you want should work. And then some additional details of cascading priority decoder to allocate multiple registers per cycles. These are, again, the idea is that if I want multiple of these registers from the register file, how can I choose those? Okay. And as I said, on a branch, the rename table are snapshots so that we can have, we can recover as fast as we want. And let me see if there's anything else that I need to. Yeah, and then like, again, you can actually, if you go back here, you will see the logic of how you can actually recover these things and put it back into the free list once there is a misprediction. I'll let you guys to look into the details of this yourself. Again, this is if you are doing the implementation of your simulator, this is where you're going to see this in a little bit more detail. I'm not going to talk about that much. And again, as I said, what we have is what we call a committed map table, and this is the actual, rat tables. That's this is the safe rat table that we're gonna have. That whenever we kind of like know that okay, these instructions are safe, we move it to that rat table, and then if we made a mistake, we go back and read it from that rat table. This is the terminology that Boom Core has. They're called committed map table. And as I said, 1 to 3, essentially the idea of 1 to 3 is again based on the destination. Whenever we know that that particular instruction has been executed, that's the time to free and put that back into the free table. Boom has this thing called PDSD to kind of detect when this is actually a free register. And again, if you go back to this logic here is actually kind of detect that whether this instruction is a type of PDSD, then and then you move it back to the free register and let it be free. Yeah, so let me see if anything else I need to say. Yeah, I guess that's pretty much it. Okay. Any questions from renaming? One thing that could be helpful for you to understand Boom specific is always reading their documentation or looking at their code. And again, if you want to go to the details of their implementation, my suggestion is like once you do your final project, you're gonna see many of these things and probably have to go back to these and read this more carefully. So again, to kind of like remind you of where we are, you're showing this simplified pipeline stage. So far, we kind of covered this part and covered this part. And as you can see, we do the ROB, but we're going to do the physical register file, the explicit one here. So from now on, we're going to talk about this part here on that. Once we kind of read the registers, what happens next, and this is what we're going to talk about in the next lecture when we're talking about the backend side of the processor. Okay. So that's pretty much it. Today, I want to kind of like finish this story by talking about these kind of units here: the backing branch predictor, the branch target buffer, and the backing predictor. This parts we kind of skipped last time. This is part of your computer assignments as well, which by the way is now on the website. Go and check it out. So for the rest of this lecture, I'm going to talking about this. Let's see if we can finish it or not. But any questions before we get to that part? All right, so let's have a 2-minute break, and then we start talking about branch prediction. All right, since we don't have much time, let's continue. So let's talk about branch prediction. And if you remember, I told you that the fetch unit takes 4 cycles during boom. The reason for this is that we do very sophisticated branch prediction, and that helps us a lot. So let's see actually what happens. Again, if you remember, I showed you this more detailed pipeline structure for the fetch unit. And as you can see, essentially what happens is that at the end of cycle 0, this is when we actually kind of feed the PC into our branch predictor. As you can see, there are kind of 2 branch predictors that we kind of like using. There is this branch target buffer, BTB, that we feed the PC to it. There's also this more of what's in their terminology backing predictor, but which is essentially another branch predictor. And this is usually, we use a combination of various different branch predictor. We use TIG, we use G-share, and you could use any other branch predictors here as well. So today, the rest of this lecture, I'm going to talk about these kind of like 3-4 units: the targets, the bimodal table, the return stack table for the RAS table, and then we're going to talk about the TIG and the G-share branch predictors and some additional things on the way. Okay, the rest of the logic here essentially is just for updating the branch predictor and all, which we already discussed. So let's actually get into the branch predictor. The first thing that you realize is essentially the input to the branch predictor is the PC. This is essentially the address of the instruction. That's like our input to any branch predictor. Another thing that you might realize is that we also feed into the branch predictor what we call the history. And this is what we remember from previous branches. The whole point of branch prediction is that we expect the branch predictor to follow some spatial or temporal history, right? Like what has been done before, most likely going to happen again. As a result, we're kind of predicting the behavior of the branch. That's why we're feeding the history, which is essentially the sequence of the outcome of the previous branches, back into our branch predictor in order to detect that. Another thing that you realize here is there's some form of hashing going on. And this hashing is essentially what it does is not necessarily directly using the history or the PC, but some weird combination of PC and the history. So we're going to actually talk about what is that hashing and why we are using that hashing, what other hashing you could use, and so on. And this part is kind of like the part that you're probably going to play with in your projects as well, kind of trying various different type of hashing, type of different history, and so on, to see which one kind of like works the best. That's really the kind of story of branch predictors when like using this different type of combinations. Okay. So let's talk about one by one. Again, as a reminder, we are looking at version 3 of Boom, which takes 4 cycles of fetch. The main reason is that we are doing all these sophisticated branch prediction. Excuse me, the original version of Boom didn't have that much of a branch predictor. It was just a simple like next line predictor. So it took only 2 cycles. So we kind of like, adding these additional things. And this is the story of most of the modern processors. Most of the modern processors use sophisticated branch prediction for performance reasons. So the version 3 is kind of like a good example of what is, a real branch prediction, like a real processor does. Okay. So what are the importance of the why branch predictor is such an important, component in a processor? There are two main reasons. One is it keeps my fetch rate as high as possible, because if I can kind of predict and kind of keep the pipeline going, then I can, keep up my IPC. The second is the accuracy of my branch predictor will help me to avoid flushing, because flush will reduce again my number of useful instruction. In other words, will reduce the IPC. So this is very important to have. That's why it's very, very important to have very accurate branch predictors. Another important part of any branch predictor is like a mechanism to be able to quickly recover things. This is something that we're not going to talk about yet. Next week, we're going to talk a little bit about recovery as well. So for any branch predictor, there are two questions that we need to answer. The first question is that what is the direction of this branch, whether this branch is taken or not taken? For example, and then in order to answer this, you have to remember that some of the branches always have just one direction. Some of them are always taken. But some are conditional, like, a branch equals anything that's kind of comparing two values and make some decisions based on those two values. You don't know. It could go either way, right? And then another thing about branches is that for not taken branches, the next address is, trivial. It's PC plus 16 or 4 or whatever the next PC is. But if the branch is taken, it could jump potentially to many, many different places in your memory, right? So essentially any address possible, it could jump onto that. So I need to figure out a mechanism to kind of not only predict the direction, but also predict the target. Because if I cannot predict the target, then the whole point of branch predictor is meaningless, all right? Another big thing about branch predictor before jumping into like the actual logics is branch predictor is just for performance, and branch predictors cannot produce correctness issues. As a result, since by nature branch prediction could cause wrong predictions, we need a mechanism for recovery, right? So we always, any branch prediction, any sort of a speculation should be coupled with some method for recoveries. You never do something that you cannot recover from. So all of these things that we say, there is always a mechanism for recovery, although we're not going to talk about the recovery mechanism today. But just keep in mind that everything here has a mechanism for recovery. You never can achieve 100% accuracy in any of these branch predictor. So you have to put in place a mechanism for recovery. But what we are really kind of banking on is this optimization for common case. That's really the whole idea of a branch predictor, that if most of the time I'm predicting correctly, then even though sometimes I need to pay extra penalty and do the recovery, I'm still going to get benefit and get performance out of the system. Okay. Another thing to remember is there is power performance trade-offs for any branch predictor. The more sophisticated the branch, it requires more area, it requires more computation. As a result, it needs more power. But a better branch predictor will probably significantly improve your performance. And again, this is where you're going to see different trade-offs. So for low-end processors, for low-power processors, you have simpler branch predictors, but as a result, you have worse performance. But for more high-end processors, you have better branch predictors. Okay. So in order to understand how many different branch predictors we need, we have to look into the type of different control flow instructions, different type of jumps or branches, okay? In general, we have kind of like 5, which is kind of like 3 actually, but let's call it 5. So the most obvious one is conditional branches. In RISC-V, this is usually starts with a word B, the character B, and then we have a bunch of different ones. So for example, BEQ, BNE, which is not equal, greater than, so on and so forth. You can actually refer to that table that I showed you in lecture 2. So these are conditional branches. The direction of the branch is unknown at the compile time because we don't know the values, that whether it's going to be like which value would be like bigger or smaller. And then the possible addresses for this branch like this is 2. It's either taken and going to jump into the label that that branch says, or it's not going to be taken, it's just continue the next instruction. So 2 possible, outcomes, 2 possible addresses, and we don't know what is the outcome unless we actually execute the instruction. Okay. Then we have this jump and link instruction, JAL. The JAL is what we call an unconditional branch, is always taken. So there is one direction all the time, and that's the taken. And as a result, there's always one specific address that we know exactly what that address is, because this is the unconditional direct branch. Okay. As kind of like, a specific type of JAL is what we call a call instruction. Call is for a function call. So it's I mean, in nature, it's exactly the same as JAL, but since it's for a specific calling a function, we usually kind of like separate it from a JAL. Then we have a return instruction, again, very similar to call. The difference between the return and call is next address could be different because you can return to any arbitrary location in your system, versus for call you always go to the beginning of that particular function. But for return, depending on where you have been called from, you could return to any other possible location. So the big difference between call and return is, for call I can predict where I go, but for return I cannot. So that's a very big difference. And then finally, the most challenging type of control flow instructions is indirect ones. The indirect one essentially jumps into whatever value that stores in the register. That's why we have this R. So usually it's kind of like JAL, R, like X3, some immediate, and that's it. And then usually there's like X0 at the beginning as well. So it means that whatever this value that's been stored in this source register, we're going to jump into that address. And since this value could be any arbitrary value, then we could jump to any places that we want. But again, what is important here is that this one is also always taken. So indirect branch is always taken. Just the address is unknown during the compile time, okay, and during the fetch time. So as you can see, essentially 4 out of 5, you know that they'll always be taken. There is one that you need to kind of predict that where it's going to go. But another thing that you need to predict is where is that next address, where we should get that next address. So essentially, this is where I said we need to predict the direction of the branch, and we also need to predict the address or the target address of a branch, okay? So what are the things that we're going to use? This is what Boom does, and as I said, many other processor does. So essentially, we're going to use a branch target buffer, or BTB. Within BTB, we have kind of like 2, and there's another one somewhere in between that I'm going to show you. So essentially, we're going to have a simple predictor that is just kind of like, yes or no kind of answer. We're going to have what we call a return address stack, or RAS. And these are all part of what we call a BTB. Then we also have a more sophisticated backing predictor, or BPD, and this is what we have, kind of like we have more logic, we have longer history, we do all these tricks in order to kind of hopefully can predict the direction of a branch a little bit better, okay? This is where all these things happens in the backing predictor, okay? So what is going on with the BTB and the branch predictor? So essentially, the branch algorithm in Boom is something like this. That first of all, the Boom gonna consult this BTB. And within this BTB, we have very simple branch predictor, which we usually call next line predictor, okay? Next or NLP. It's not the other, it's not the famous NLP. This is computer architecture NLP. NLP is essentially, think about it as a combination of just the history of addresses, a RAS, and a bimodal table. And then for non-branch instructions, of course, you don't need to do anything. So essentially, the outcome of this is something garbage that you can safely ignore, because not many all the instructions are branch instructions, right? Then what we do is we also consult our more sophisticated branch, and we're gonna get kind of like a direction and some opinion from that. And what we get from this and what we get from this necessarily not be the same thing. So for example, your sophisticated branch predictor would say not taken. Your kind of simple branch predictor might say taken, okay? So now you're faced with this fundamental question of what should we do? And then what we need to kind of like, decide who should take the precedence. This is a design decision. Most of the cases, we're gonna, rely on a more sophisticated branch predictor, because of course we have the sophisticated branch predictor because we are assuming it's more accurate. Otherwise, what's the point? But one thing that many design does, they have this what they call tournament predictor, which they have many different branch predictors, and then based on some dynamic metric, they decide which one to choose. So we're gonna actually show you later that tournament predictors. But think about this is that if I have some metric of accuracy of this guy and have some metric of accuracy of this other one, and then I can dynamically see which one is more accurate in the past, let's say 10 branches, then I can use that one, right? So usually this dynamic situation has been very commonly used in many of these modern processors. But of course, what makes sense is most of the time your sophisticated branch predictor should work better, okay? Otherwise, it doesn't make any sense. Let's just start with this smaller, more straightforward next line predictor kind of thing, and then let's talk about a more sophisticated branch predictor, okay? So the first thing that happens is you feed the PC in order to see whether your branch has been seen before or not. Because again, the whole point of a branch predictor is we're gonna, bank on this fact that we have seen branch before, we know their operation, their behavior, and based on that, we're gonna predict, okay? So we're gonna feed this PC and we're gonna scan this table of tags that we store for this PC. How do we store that tags? Think about this as you can just store the actual PC into your BTB. That would be the most simple way of remembering all those. Storing the entire PC might be a little bit difficult because PC is like 32-bit number, like a huge number that you need to store. So you may want to kind of only store like few bits of your PC, like lower bits, middle bits, higher bits. There are other tricks that you can use. Maybe you can kind of like XOR half and the bottom half and lower half together, and then have that as a tag. You can use different tricks in order to save the tag. Of course, if your tag is smaller than the size of PC, we're going to have the problem of collision, right? That there could be a PC that maps to a tag, or there could be a tag that maps to multiple PCs. Again, that could be a possibility, but that's not gonna create a huge problem, because worst case scenario, you're gonna just incorrectly think that you have seen that branch before, and you're gonna make a prediction based on that. Either your prediction will be right or wrong. If you get lucky, it might be right. If you get unlucky, it might be wrong. But as I said, we always have a mechanism to recover things, okay? So worst case scenario, if you have collision and all those things, we can always recover, okay? So the first thing we do is we see that whether we have seen this branch or not. If we didn't see it and we haven't seen it, then nothing we can do, right? So we can just, move forward. If we have seen it, then we can do all these other tricks in order to see what is the target, okay? So once we see that, if there is a match and it's a valid, so this is it's a match and it's valid, then we're gonna kind of like see whether we can kind of predict what this is, okay? The second thing that we're gonna check is whether this is a return instruction or not. And this is what we call a return address stack or RAS, which is kind of like this column here. You can actually think about it as a separate table, but usually these are all integrated within one. So this return basically telling you that whether this is a return instruction or not, because the good thing about return instruction is that you can use some form of a FIFO method to kind of like, because there is a call and there is a return. If there is a return, there has been a call previously. So I can actually remember where that call was coming from, and my return address could be always pointing to that, right? So whenever I see a call, I push the address for the return, and that's how we're gonna actually remember that, okay? If it's not a return instruction, then we're gonna see whether this is an unconditional jump instruction. If it's an unconditional jump instruction, again, we don't need to predict the direction. We always know that this is going to be taken. So we're going to kind of, skip this part, which is kind of the direction part, and directly go and see the target. If it's not return and it's not a jump, this is a conditional branch or this is an indirect branch. That's where we're going to see this, what we call a bimodal predictor, which is essentially, think about it as a 0-1 bits. 1 means taken and 0 means not taken. And you can save that as kind of the history. Last time I saw this, was it taken or was it not taken? This is the number I'm going to store. And then based on that, I'm going to just pick the target. Okay. So these are the kind of things that we're going to use in our next line predictor, simple branch predictor. This part is what we call a BIM. This part is what we call a RAS. And this part is generally what we refer as to the BTP. Question.
Is
Yeah.
val valid?
Yes, val is valid. So it means that, is it like, is this really like, filled out by us? Or was it like from some previous old instruction? All right. So let me talk a little bit more about this BIM, because this BIM is a little bit, it could be optimized a little bit more. So this BIDX is the branch index, okay? So essentially it tells you that which instruction within that fetch packet is actually indeed the branch. Because remember that you're reading, for example, 4 instructions at a time, and not necessarily all of them would be a branch. So this kind of saves which of these are indeed a branch, okay? Because we could have many different instructions, and you need to know which of them was indeed the relevant PC and mask the others. Or sometimes you could have multiple branches in your 4 instructions. So this is actually telling you which one to look at for each of these units. Sorry, before jumping into the to the bimodal, let me quickly talk about the return. As I said, the idea of the return or RAS is that if we call, we should return. So whenever we see a call, we save the address. Okay, so we can have like a last in first out kind of structure that we push it into the stack and we kind of pop it from the stack. Okay, and the good thing about this is that it's very accurate, right? Because call and returns always happens in tandem to each other. The question would be like, when do we update the RAS? And we update the RAS when we decode the instruction. When we see that this is indeed a call, that's when we go back into our BTB and say that, oh, this was a call, so save this address for the return instruction. Okay. And then we need to pop it from the RAS as well, of course, because if you don't pop it, then next time that you have a call, you're gonna incorrectly predict it. So it's like a regular stack. You push and pop if you see a call and a return. Okay. So one big question is, what will happen when RAS is full? What should we do? Any suggestions? So if you have many calls, then what should we do? Well, one simple solution is a stalling. Any other solutions you might think of that could save us? Use a bigger RAS, sure. let's say we kind of max out on the size of the RAS, what should we do? Think about why would we kind of, fill our RAS? What are the scenarios that you think your RAS gets filled quickly? What sort of codes could cause your RAS to fill? Recursive, okay? So in that case, what do you think would be a good optimization?
Force a return.
What's that?
Well, I mean, I wouldn't call it an optimization, but you could force a return and set up it somewhere and
How do you force a return?
go to the top of the RAS. Like
Okay.
return the disk there and then set a bit somewhere that says. Hey, this didn't work and then crash it.
Okay, what were you?
Maybe like. Cause it's recursive, so it will always return to the same address, so.
Mhm.
If you notice that you get a bunch of recursion, then maybe. Like somehow put it into the BTB
Mhm.
itself.
Mhm.
So that there's only just one return,
Mhm.
you don't have to go back to the RAS.
Yeah, so you want to add something?
Well, I was just gonna say remove the first, like the earliest items.
Yeah, so essentially you need to keep the last, right? If it's a recursive, it always jumps into the same address over and over. So if I have something like this, that boom, 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 I'm adding things to it. And then essentially if it's a recursive, all of them are the same thing. So I pop, pop, pop. And then what I can do is that I can actually keep the last one and no longer pushing things into it because all of them are jumping back to the same one over and over, right? So essentially all I need to do is at some point if I see it's full, I keep the last one and then remove the rest and have space for the other instructions, or no longer push into the stack. I'm just keeping the last one over and over and over. Okay, so this is kind of like, this is the way that we can kind of fix the recursive. Yes.
How when encountering a recursion?
It doesn't know. We can have logic to predict that, but we anticipate that if you're quickly filling, it's probably because of recursion. So once it gets full, we switch to this logic. If that makes sense.
We need to know how far it can go, right? How far it can remove the. How back it can go and remove the addresses, right?
No. So what I'm saying is that let's say your RAS gets full, right? So now your next instruction comes, okay? Instead of pushing it into the RAS, what you can do is saying that, oh, I think this is a recursive function. As a result, I'm not gonna push it, but next time I see the return, I'm gonna pop it from the top. Okay, because it's the same, it might be the same call. I mean, again, it might be wrong and it might be a different call, but again, you recover. But then you don't also pop this, you just count the numbers that you didn't. So maybe you have another counter here that's kind of see how many you didn't push, then you don't pop, and then you go back to at some point you go pop, 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 and then you're good to go. Something like that. Yes.
So what happens like if it's like a recursion, but then like, for example, in your base case, you call a different function. And
Mhm.
then it needs to update the RAS, but then it just doesn't update.
It doesn't update, so it's a misprediction. So it's just, worst case scenario, you just think that this is the correct address and it's not, and then you pay the penalty. Yeah, so this is kind of like, and then of course, another simpler option is you just wrap around. When it's full, say that, okay, I'm gonna just kind of continue overwriting from the bottom, right? So at least keep the kind of younger ones there, but I'm gonna overwrite. And then at least like in near term, I'm gonna get good performance. In long term, I'm not gonna get a good performance. So these are different things that you can do. Okay. So this is the story of RAS. RAS is commonly used in almost all the processors. As I said, if it's a direct jump, then we're gonna use the target address. We're gonna use this jump column inside our VTB, and based on that, we're gonna go to the target and use that target, right? And again, the idea is that we have seen this branch before, That's why this works. For indirect branches, this is not a good idea though, right? Because you can have many, many different addresses. But again, who cares? It's just a misprediction. And by the way, there are actually methods for indirect branches as well, which we're not going to talk about. But just keep that in mind. As I said, usually what we do is that we need to store the tag somehow into our BTB, into our kind of target address. There are many, many different ways that you could do that. You can, as I said, you can kind of like use half of your PC, and this is your PC. You can use some portion of your PC as a tag. You can use the entire PC as a tag. You can kind of divide your PC as index plus tag and then use that. So you can use many different ways of addressing a BTB. Usually the common way that people do it is they use the PC, they divide PC into index and tag, lower bits to kind of index the table, and then the rest to store the tag. The index usually don't directly go and index the table. We usually use some form of hashing to address that. The reason for hashing is to kind of like, randomize the behavior of the tag so that we reduce the kind of conflict misses inside the tag. Once again, when we're talking about the caches, you will see that why hashing is a good idea to access any sort of cache structure. So as I said, there are different options. You can use directly, you can combination of higher and lower bits, and so on and so forth. Of course, if you use lower bits, you're banking on the fact that we're going to have spatial locality because, we see this over and over. When you're combining bits, you're more of assuming that this is a more general branch prediction behavior. So that's kind of like works for almost every instruction in your system. So there are different trade-offs when you're doing this. All right, so one question before we jump into the bimodal one is, what will happen if we don't see that branch? Okay, if the branch is not there, there are two options that we can do. We either can stall, okay, we say that, okay, we don't know whether this branch is taken or not taken, we don't know the target. So what we're going to do is that we're not going to predict anything, okay? The second option is that you can predict not taken and then continue the path, right? Because if you predict not taken, you don't need the target address, you just continue. And then the idea would be that this would be mostly wrong in many cases, but there is also something. So can you give me kind of the pros and cons of each approach? What do you think, which one would you choose and why? Would you stall your processor to know the outcome, or would you continue not taking and then you might make a mistake and you have to recover? Yeah.
Stalling, you basically don't even have the opportunity to get lucky.
Mm-hmm.
So from that perspective, it might seem beneficial to.
Okay, but you also don't need to recover.
That's true.
Yeah.
How much time, what's the time, the cycle time for recovery versus cycle time for stalling, how long do you have to wait?
I don't know, you tell me.
Like,
What do you think would be beneficial?
probably calculate it out in
Uh-huh.
percentage of how long the penalty will be for flushing
Uh-huh.
versus like, versus stalling.
Uh-huh.
And multiply that by
Uh-huh.
the percentage of you being correct, you can figure out.
Okay, which one is beneficial? Sure. You want to add something?
Yeah, well, I was gonna kind of touch on the same point where you would have to see how long you would have to stall for, like how many cycles it would take
Mm-hmm.
for you to actually determine which path to take. Or
Mhm.
how that compares to how long it would take you
Mhm.
to recover from the next prediction.
Sure. Anybody else wants to add? Yeah.
In this case, you can take the not taken part, the unnecessary computing,
Unnecessary computing, yeah. So that's
security one.
security vulnerability could be one thing, could be power consumption as well. So if you probably in your like watch or your iPad, you probably want to stall, and it saves you a little bit of power, right? Even if it might result in lower performance. So there are all good points. So there is no one answer, as you can see. depends on the processor design, depends on how lucky you get, right? Or how unlucky you might get. So these are the things that when you're designing a processor, you have to think of what is my workload, what are my constraints, what does my market architecture look like, how fast I can recover, when do I know the outcome, and all those things, okay? So there is no one single answer to this. It's always design decisions that you need to do some analysis first and then make a decision, okay? Any questions, comments? Yeah.
When you say the address is not there, does it mean that it's not there initially, or is it like it has been removed from the?
Oh, it's either removed or it's not there. We don't know why, but it's not there. It could be like a previous branch that we have seen, but we have limited space in our BTB and someone kicked this out, or it could be it's just the first time we really see this branch. Either case, we don't know what we don't know, right? So it's not there. Okay, so now there's kind of like, we know about these kind of basic ones. We know if it's a return, what should we do? If it's a unconditional branch, what should we do? Now let's talk about the conditional ones. That's kind of like the big deal for us. What we need to predict is the direction, right? So we need to know whether this branch is taken or not taken, and then continue. Of course, you can start with like very simple ideas such as, okay, we always predict not taken. We just don't care. It's like whenever you see the direction, we just take it easy and say, okay, not taken. Or you can do it the other way around. You can always predict taken. There is always trade-offs with this strategies, right? Another thing that we can do is we can use this BTF and a strategy that is backward taken, forward not taken, because essentially most of the backward branches are taken. Okay, when you like think about for loops, while loops, these are all backward branches, right? So you do things and then you jump back. You do things and then you jump back, right? It's not always the same. There's one time that the condition is not true and you continue. But if, for example, you do 400 times, something like that, most of the cases, your backward branches are taken. So that's a good thing. And your forward branch is usually not taken, right? So it's the same story that, if something, then you move forward. So this is actually something that many compilers do for optimization, like many branch predictors do as well. Another thing, as I said, you can do always taken or not taken, because I think like more than 50% are taken branches in general. So if you go by taken, you're better than just random prediction. And then you can also do heuristic or profiling. You can run your program one time and see what is the behavior. And then you can save this number somewhere. And then next time that you run it, you use usually this, what we call predicates. And these predicates can kind of give some form of direction to the branch predictor that, we run this one time and we saw this observation, like this behavior, probably going to see the same. So good things about this static time, prediction is that it makes your hardware very simple because you don't really need a sophisticated branch predictor. You can go by a very simple branch predictor, you get some decent prediction. But of course, nothing beats dynamic time in terms of prediction. During the dynamic time, the idea is very simple, that you kind of like, take some features from the system. Usually this is a history. And then you use some function. So this function could be, I don't know, just XORing all the bits of history, could be looking at some tables, could be various different things. And then you predict an outcome. And your outcome is very simple, 0 or 1, right? 0 not taken, 1 is taken. And then what are those features? We're going to discuss that essentially in the next few slides. Usually the features that we're going to use is the PC address, the branch history, correlation with some other branches, and many other things. And as you can see, one thing when you see function features outcome, the first thing that comes to mind is some form of machine learning, right? Like, if you have a feature, you want to fit a function to that, this just, screams machine learning as well. And as you can predict, machine learning has been like heavily used in branch predictors as well, which we're going to talk a little bit about in this lecture as well. All right, so let's do dynamic prediction, and then let's start with a very, very simple one. And this is what we call a bimodal table, or BIM. This is the first thing that Boom also use. So when it sees a branch, it feeds it into the BTB, and the BTB, what it does is that it checks with that table that I showed you. If it's there, then we're good to go. If it's not there, you're gonna ask whether Beam has any idea what this is. Is it whether this is a conditional branch or not? And then the BIM is just this simple table that kind of remembers what did we do last time, 0 or 1, okay, 1 bit. And then we basically saying that if the last time the branch was taken, very likely that this time it's going to also be taken, okay? So this is kind of like, this is how we're going to do it. So we usually call this a branch history table or BHT. We see the address, we ask the direction, and then if the direction says taken, we take this address. If the direction says not taken, we don't take this address, we just move forward, right? And then the idea is 1 bit might be too small, okay? That's why we usually use, we add some what we call hysteresis, some resistance to a branch. Essentially, the idea is that if the last time was taken, but if the last 2 times was taken, then it's very, very likely that this time is also going to be taken. If the last time was taken and the previous time before that was not taken, then we are not sure. It could be taken, it could be not taken. But if both of the times were not taken, then it's again very, very likely that's not going to be taken. Okay, so we're going to have some form of state machine like this, that we are either in like strongly taken or strongly not taken, regime, and like 0, 0, or 1, 1. If you're in 1, 1, we predict taken. If you're in 0, 0, we predict not taken. If you're in kind of the weak side, then we kind of say that, okay, last one, we kind of give a little bit more edge. So if the very last time was taken, we're going to predict taken. But we are not sure. We are open to change our mind the next time. So, for example, if you're in 1, 0, which means that the very last time was taken, but the one time before that was not taken, if we see that this time is indeed taken, then we see that, okay, the last 2 times are taken. So let's actually move to the stronger side. If we see that, oh, we predict taken, but in fact it was not taken, then we're going to move into strong not taken. Okay, and the same story for 0, 1. If we last time we saw not taken, and the time before that it was taken, we are in 0, 1. If we see it's not taken, we're going to go here. If we see taken, we're going to go here. Okay, so the idea here basically is that we're going to always kind of prioritize what we saw the previous time, but we're going to add a little bit of hysteresis to it so that we can change things if need be. Okay. You might ask why 2-bit, why not like 4-bit or 5-bit? People have looked at this for the longest time, and what they saw is that like 2 bits is actually giving you kind of the best performance versus storage. Like adding an extra bit doesn't really help that much that you think. Yes.
Is there a benefit to doing this sort of encoding over just simple counting?
Simple counting as in?
I mean, if you look at the numbers as binary, it would go from 0 to 1 to 3.
Yeah.
So like, why not just have 2 intermediary stages in your state machine and just make it basically linear?
Yeah, it's this is linear in some sense. So it's just think about this 2 bits, right? So this 2 bits tells you what you have done, right? So if you are 0, 1 and then you see 1, you go there. If you so you essentially just a simple counter of 0, 0, 0, 1 or 1, 1 or 1, 0. I mean, the implementation of this is just a simple counter anyway. You just add or remove, and then you flip into one of the 2 stages. That's all you need. Right.
I mean, it is, I forgot the name of the encoding, but basically
You mean one hot kind of thing?
sorta, but you're basically just flipping 1 bit at a time instead of 2.
Well, this is also always 1 bit, right? So from 1, 0, you go to 0, 0, 1 bit, or go to 0, 1, 1 bit, or go to 1, 1, 1 bit. You always just change 1 bit.
Yeah.
All right. Any other questions? Cool. Yes.
From weekly taken to weekly not taken.
From here to here, you can do that, and many people does that. Usually the way to do it, so this depends on like the strategy. Typically, people suggest from weekly not taken, just go to directly taken. Like, if you see enough evidence, then you go to strongly. But yeah, nothing prevents you of going this way as well. Yeah. So this is what we call a bimodal because it's bimodal. Think about it as essentially instead of like having a table of 1 bit, now we have a table of 2 bits, right? We usually call this prediction bit and call this hysteresis bit because as you can see, essentially this bit tells you whether this is taken or not taken, right? So if it's here, we're going to predict taken. If it's here, we're going to predict not taken. And this is kind of just to give you a little bit of more resistance to the changes. So we usually, at least in boom core terminology, we call this p-bit that just predict what it is. So for every branch, we need to read this, right, to make a prediction. We only write to this when a misprediction occurs, right? The H bit is the hysteresis bit. We only read this during the misprediction, and we write this when the branch is resolved to update it, right? So good thing about this is that basically all you need to do for a branch predictor is just reading 1 bit. And this is very fast when we're designing this in our systems. And we only need to read this one during the update section, so in the back end of the process. So during the fetch, all you really need is just this 1 column of this table. Although this is like a 2-bit, you still just need to read 1 bit, which is good. Okay. So when do we update the bimodal? We update when we know the actual outcome, right? So once we know that whether indeed this was taken or not taken, you have to go back and update your history, because next time that you are reading this, you need to know the correct history. If you don't update, then you're basically not doing the correct, not doing it correctly. So usually we do this in the front end still, the branch redirected, using the branch unit in the later stage of the BPD. So essentially, if you remember the 4 stages, in the 4th stage, we know already whether this branch is taken or not taken. Then we can actually kind of update our BTB. And then, of course, if there is no entry into the BTB for this branch, we create and allocate a new entry. And then if you need to kind of kick out something, then we need a replacement policy of what to kick out. Usually it's doing some age, like, what was the last thing that we kicked it out, like, we inserted, or you can just use direct mapping and all those techniques that we discuss in regular cache. All right, so now there are questions of how do we optimize this, and the rest of the story of a branch predictor is taking this 2-bit branch predictor and try to do all this crazy stuff in order to make it more sophisticated, more accurate, okay? So the story of branch predictor really is just starting off of this bimodal, which is kind of introduced in the early 90s, and adding all this sort of complexity of adding more history, adding more complexity and all those things. So how should we do that? So these are kind of the questions that we need to answer. So do we need 1 table per branch, or should we kind of reuse the tables for all the branches? Okay, so one idea would be that if I want to remember the history, one thing I could do is that saying that for every unique branch, I have 1 table, right? And this probably would be the best, because then I can independently track things. But the problem with that would be 2 things. One is you have a lot of storage. And the second thing is you have no idea about your surrounding branches, because sometimes there's correlation between branches, okay? So on the other extreme, you can have just 1 table for all the branches. So whenever you see a conditional branch, you go and see what was the last thing that we did for any other branch, and use that for the prediction, okay? So this is one extreme, that you have one separate table for every branch, and then the other extreme is that having just one table for all the branches. And then of course there will be something in between, which you can, for example, have one table that's kind of shared between some of the branches, but not shared between other branches. And if you have that, we need to kind of like think about how do we do this sharing? What's the right way of doing the sharing, and what's a good idea to do that? Let's see after actually if you have any suggestions.
Where
Yeah.
exactly is the table stored in the hardware?
Where exactly is the table stored? This actually is part of the pipeline processors. Think about where the BTB is stored, part of the fetch, like the same way that you store your register file, you store this as well. So it's stored as some flip-flops, like a bank of registers kind of thing.
It does not take space in the main memory. It's separate.
No, usually you don't want to put it in the main memory, because if you put it in the main memory, then it defeats it. You want to access it as quickly as possible. So what do you think what should we use as the history? What do you think we should be kind of like doing for the prediction? So here's the two things that we need to do, and people do. So the first thing is you should use the previous history of that particular branch, okay? If we see this branch multiple times, maybe we can like remember its history. And this is what we call the local history. That is, that particular branch, let's say we saw it 10 times, and the past 10 times, like five times it was taken, 5 times it was not taken. So we're gonna get something like, I don't know, 1 0 1 1 0 1 0 something, right? So this is the local history of that particular branch. Then we're gonna have what we call the global history. The global history is the history of all the branches. So the last 10 branches, for example, here is the kind of like, the behavior of the last 10 branches. And this is what we call the global history. That is like not that particular branch, but all the branches that we have seen. The reason that both of these are important is that, of course, each branch history is important, because if you, for example, always taken for that branch, very likely that branch is going to continue to be taken. But another thing that people have found out was behavior of the program itself has an impact on the local branches. Because, for example, if you're calling a function, okay, and then you do some branches within that function, that's your local history, right? But if I call this function from function A versus if I call this function from function B, the behavior might be slightly different, because the input that I send from A might be different from the input that I send from B. And as a result, what used to be like always taken with this branch for some result, maybe like all the results that A is sending to this function is always like small values or large values, but B value is like kind of just exactly the different, opposite. So that's why we kind of say that, okay, we also take a look at the global history, like the things that we are currently doing that kind of tells us whether this has been called from A or whether this has been called from B. And based on that, we kind of adjust. Okay, that's kind of like the main idea behind these branch predictors, that we don't just focus on kind of our short-term behavior, but we also have kind of more of a global level behavior. And the idea is that the global also tells us something about this branch. Now, the fundamental idea and the fundamental question is, how much of a global and how much of a local should I mix? Should I prioritize local over global? Should be half-half? Should be more global and less local? What is the right way of mixing these two? And this is the story of different branch predictors. This is probably what you're going to do in your computer assignments as well. They're going to try different things and see which one will work. Okay. So the global one, we usually store it in a register called Global History Register, GHR. GHR, just thinking about is that registers of size n, that you store the last n outcome of the branch. And then this is a binary values, right? So for example, let's say n is equal to 32. Essentially, you store a 32-bit binary number. It's kind of like something like this, okay? That this is the last n branches that I see in this program. I store it like this, and this is kind of like a circular, right? So this is the oldest, this is the newest. Once a new comes, everything kind of shift to the left, and then this last one is kind of go out, and then we kind of keep doing it. Yeah.
Why do we need to store 32? I mean, we are considering only the global history, so latest global history, or are we taking again from there? We are doing some kind of normalization.
So it's saying y is 32?
Yeah.
It's just arbitrary number. It's saying n. So n could be 32, could be thousands.
When we are making a decision for current branch, and
Uh-huh.
we have to make use of the global history also,
Mm-hmm.
shouldn't it only be the latest global history, or are we like taking why 32 global histories?
Oh, why you are asking why is it too long?
But why do we need to take consider previous histories? I mean, shouldn't it be just the latest previous history?
Well, because of these two things that I'm showing here, right? So your latest is your local, right? So your latest kind of like the behavior, not necessarily. So your latest is like a few bits here, like 4 bits, let's say. Yes, you can do 4. Actually, what you will see is that the longer the history, the better. Because, for example, let's say you have a function call and then another function call, or you have a for loop and then another for loop. And then if you just remember the last 4, what you're really looking at is the behavior of this function and not this function. So they could be completely decorrelated from each other. So there is value of remembering longer periods, because the chances that you find something that is indeed correlated becomes higher. If you just look at the very, very recent one, the very recent one could be as just a completely separate function that you just call and then you are returning. So it's a trade-off between like whether it makes sense to do just the recent one or more longer history.
Is it similar to what we saw the hysteresis one?
In what sense?
I mean, like I mean, here also we are having some kind of like states here based on the state that it was taken, then like 2 times it was taken, then only we'll consider it taken on.
Mm-hmm. Yeah, I'm gonna actually show you how we're gonna use this GSJR to do the prediction. Yeah.
Yeah, so when you say last n branches, is like any branches from?
Any branches. This is global. So across the board from this particular application, here's the last n branches, and here's the outcome of those last n branches. We're going to store it into this GSJAR register. Okay. And then, so based on this, we're going to have this table, and this is what we call G-share prediction. Okay, this is a very famous and very popular type of branch predictor, which the reason it's called G-share is kind of sharing the global with all the local ones. So this is our kind of old bimodal. Okay, so here's what we're going to do. We're going to take the global history. This is the register that I talked about. Let's say this is 4-bit for now. Okay, now we take our PC. Okay, remember that in order to access this table, we were using PC, right? So instead of directly using PC to access this, what we're going to do now is that we're going to XOR global history with PC. All right, we're going to create kind of some form of a hashing, and then we're going to access this. The idea here is that global history and the PC, if there is some form of correlation between what has been done before and the branch that we are looking at, this should give us that kind of correlation. Okay, so we are XORing this to then go to our bimodal and then bring that out. And this is what we call a G-share, because essentially, if you're looking at the same PC over and over, if you're looking at the same branch over and over, if the global history stays the same, we're going to go to the same entry. If the global history changes, then we're actually going to go to a different entry. Same story as the PC. If the global history stays the same, but the branch is changing, again, this XOR value will change and we're going to go to the different entry. So this way, we're kind of balancing between local history and the global history. If the global history is changing, then we are changing the entry. If local history is changing, we are changing the entry. Okay. And then here we just use the old bimodal predictor. Okay. And how many entries does this have? This depends on how much storage you want to use. The bigger this is, the more bits here and here we are using, right? The smaller this is, then you need to do more of XOR. Also, again, this is kind of like the idea that you need to do the trade-off to see what's the good size to achieve a good performance. Okay?
This will predict whether it will take or not.
Yes, and this is all for prediction of the direction. So we're talking about conditional
Where
branching.
will we get the address from?
So this is always coupled with a BTB, right? So this each entry of this has the target address with.
But it's still possible that, I mean, PC, when we do PC with the global history, we come to a value which has a hash value present, but it may not have the correct address.
Yeah, it's because you just pick a wrong branch. So you might accidentally hit, but it's not really that branch, it's some other branch. So there is, as I said, there is always the collision problem, which yes, if you have enough entry for every single branch, then you won't have, but since you have limited storage, you will have collision.
So the global history is just like a shift register, right?
Yes.
Okay, so like picture like a if statement instead of a for loop. You and you say you're constantly taking that, you're basically just like putting a bunch of race entries in your counter table, right? Because you would be shifting values in as you enter that for loop and hit that if statement and say like there's a branch here, and then your global history would change
Mm-hmm.
as you move through.
Mm-hmm.
You'd slowly get all ones.
Yeah.
Except with the program counter, which is going to stay the same for each different branch,
Mm-hmm.
and.
Yeah. So you're gonna like repeated entries if you see the same branch you're saying?
You have a bunch of different entries that aren't in your counter table, and I would assume you then add them to your counter table,
Uh-huh.
and that's, you're never going to go back to those.
Well, I mean, if you're going back over and over, at some point you're gonna see the repeated. Actually, that's exactly what you want, right? So if you have, like, let's say you have if statement, so you're saying that like it's something like a for loop and an if statement inside,
Yeah.
right? So your PC always stays the same, right?
Yeah.
And then what you're saying is that let's say this is 1000, and then I'm just keep like want to predict this, right? So and then let's say my global history is, I don't know, 000 at the beginning, right? Then the next time would be 001 and then 0010 and so on and so forth, right? So sorry, 111 and then 1111 at some point. So then the first four entries would be all this if statement, right?
Yeah.
And then what the good thing, actually, this is very good, right? Because then I keep seeing 111 and then I'm going to keep hitting on this. Actually, if I have reuse, this is perfect. Yes, I'm gonna like these three are gonna be kind of useless, but eventually I'm gonna hit on something that I really like. And actually, if I have reuse and I have a very predictable behavior, this is great. But now think about this alternative scenario that if this branch is kind of taken, not taken, then this G-share can actually help you a lot, because then you're gonna have something like this. And then this actually gonna then give you the exact table that you want to see, because you're kind of flipping between the two. So you're kind of like reading from two bimodal tables each time, and that exactly give you what you want to do, right? So it's kind of like you're always shifting between this and this, right? And these are looking at two different bimodal tables. Both, one says always taken, one says always not taken. And that's what you want.
And. Yeah, so as long as your global history is not too long, it's probably.
Yeah, and then even it's you know, yes, it's not too long. That's true. There are other optimizations that you can fix that issue. But just keep in mind that if your branch actually, like, you know, if your global history, like let's say if your branch is taken, not taken, That's also very good with your global history because then you have 4 tables, 2 of them says taken, 2 of them says not taken. So you can think about actually if your branch has kind of like weird pattern of like 3 taken, 1 not taken, your global history can actually track it very well and then actually point you to the right table. Yes.
It's like, it seems like intuitively, it would be pretty rare to have like, if you have like 32
Mm-hmm.
bit history, it seems like it would be pretty rare for there to be like the exact same history. Apart from these like big 4 loops. So I was wondering like, is it actually like very common to have that?
Well, I mean, so think about this, that you're gonna get good performance out of your branch predictor if you keep seeing the same branch. If you're seeing the branch once, then you are kind of shooting in the dark kind of thing, right? So the whole purpose of branch predictor is if you see a branch over and over, you should be able to predict it correct most of the time. So if there's like, oh, there's one tiny if statement at the beginning of my function and never come back to it, then sure, then it's just a random behavior and the random branch. So essentially what you're predicting is the average behavior of your program. That's really what you're going to predict for this one branch.
But like, what if like you go to that branch a lot, but like your start point is not always exactly the same?
Well, in that case, then your history kind of, that's why you also use your PC, right? Because the PC also has some impact on this G share. So it's not just the global history, it's also PC. So the PC kind of, your global history is not like changing significantly to the left and right. Your PC is kind of like dictate what addresses or what range of addresses it's gonna go to. So it's not just the global history, it's combination of PC and global history that gives you the right table.
But like, isn't there like a different entry though? Like, so like, even if the PC sort of like is similar, it wouldn't check, well, it would still create a new entry.
It won, right? So like, let's say I have this as my global history, right? And then let's say that my next 2 branches is also taken, not taken. So my global history stays the same. And then if my PC is the same PC, I'm going to see exact same thing over and over again, right? So it's not like global history could be like any arbitrary numbers. It's kind of follows some patterns. And if that pattern is kind of repetitive, you're going to see the same branch over and over again, right? Because think about this, is that if you have your if and your if is part of some repetitive behavior, your global history also going to repeat itself. So as a result, whenever you hit this, you're going to see the exact same global history and exact same PC. You're going to end up in the exact same branch table, right? Again, if it's predictable behavior, it's a repetitive and predictable behavior, the branch predictor will catch it. If it's completely random, then it's not magic, right? So your branch predictor won't predict it. So that's the whole idea. Cool. So this is just to finish this story. This is how G-share is implemented in Boom. As you can see, this is the PC, this is the history, this is the hash that essentially that same XOR I told you. This is the counter table, this is the data that goes. And then as you can see from the later stage of the pipeline, this table will be updated because once we see the outcome, we need to update this table. The results goes to some form of a buffer that's going to be used in later stage of the pipeline. And then as you can see, the history is also like this circular, shift register. That's kind of like one goes in, one goes out. And then that's how we're going to actually use the history. Okay. This is how we are implementing in Boom. All right. So we have to talk about the optimizations of TIG and so on. Don't forget that, your computer assignment 1 is out. Which is about branch predictors. Start working on it and start thinking about it, and we're gonna finish this next week. Okay.